Hello everyone, welcome back to Science Sketchbook. Today I'm going to show you 4 quick steps to finding the R or S configuration of a chiral center. In this video, I'm going to be sharing a little trick that will help you get the right answer every time. At the end, I've got some challenge problems for you as well, so don't forget to stay for those too. Alright, quick reminder. To find the R and S configuration, you need a chiral center, which is just an atom with 4 unique groups sticking off of it. For organic chemistry 1, it's usually just a carbon. This will give the molecule a sort of left or right-handed spin. The right spin is R and the left spin is S. Alright, look at that example molecule. It has 4 unique entire groups coming off of it. A fluorine, an alcohol group, a methyl or 1-carbon group, and an ethyl or 2-carbon group. Let's use this chiral center to work out the 4 major steps of finding the R and S configuration. 1. You're going to rank those 4 groups by highest atomic weight, and super crucial, the weight at the very first point of difference. Sketch here is emphasizing not the total mass of each group, only atoms within 1 bond length away at a time. So for example, not the entire mass of the 2-carbon chain to the right there, it's just the immediate first carbon. So look, here are the very first atoms 1 bond length away from the chiral center. You've got fluorine, oxygen, carbon, and carbon. Which is the heaviest atom? Yeah, fluorine. On a periodic table, fluorine is about 19 AMU, oxygen is about 15, and carbon is about 12. So you can go ahead and give it the number 1, and oxygen being next heaviest gets number 2. Now, what's heavier, carbon or carbon? Neither, it's the same, so we need a tiebreaker. Move 1 bond length down to see the next point of difference. Seems these atoms have a few things connected within 1 bond length, so you'll have to consider all 3 to see who got to something heavier first. The carbon on the left is immediately bonded to 3 hydrogens, pretty lame already. The one on the right has 2 hydrogens but 1 carbon. So look at the 3 on each side. You can kind of view them like cards in poker or something. Essentially, see who has the winning hand. In this case, whose hand got to something heavier first. Again, you're not taking the sum of masses at the point of difference either. You're just looking for the first one to include a higher weighted atom. Looks like that side to the right got to something heavier first, that extra carbon. So that'll be the next priority, and the methyl will be the last one. Note that I was careful to draw the rank numbers close to the original chiral center so it's easier to find the spin later. If you draw things a bit too far along the chain, it can get messed up. So, that's step 1. You've ranked your groups. Step 2 is to find the spin like a clock. To do that, you must hide the dash and then trace the numbers. Hiding what's in back minimizes any weird out-of-order numbers. In this case, everything's fine. It seems to be in number order already, but very often it'll end up with a weird order. See, if I just happen to draw it like that, where by chance I just drew that wedged fluorine pointing to the right, the numeric order looks odd, right? Would you go 1, 3, 4, 2 or 1, 2, 4, 3? Just hide the dashed number to always have a clear numeric order. Go 1 to 3 to 4, and that's going to the right in a circle like this. That leads into step 3. Check if that arrow points clockwise as in to the right. That'll make your answer R. Or counterclockwise as in left for S. This is clockwise, right? So that's R. Now, the very important step 4, this is the essential trick. At the end, you must check the dash again. Is 1 or 3 in the back? If so, you flip your answer. Keep in mind when I say check the dash, it must be the dash immediately coming off of the chiral center you're testing. So in this molecule, it'd be where the hydroxy group is. If you're wondering why do we do this trick, some groups just need to not be in the back. Using this trick is easier than repositioning the molecule. Otherwise, you have to either redraw the molecule or spatially maneuver it in your head, and that can lead to error. In this example, rank 2 is dashed in back there, so we are A-OK, no need to flip. The final answer remains R. Ready for a harder example? Let's try this guy. Alright, first of all, how many chiral centers are we working with? Well, this carbon here has a hydrogen that was implied, a methyl group, and one side of the ring goes to a double bond and the other to some normal carbons, so that's 4 groups. The carbon below has a hydrogen, a tert-butyl group, and also that split between the double bond carbon and the regular carbons. So that's 1 too. Thus, we've got 2 chiral centers, each with their own configuration. Let's try out the 4 steps. What was step 1? Yeah, this is the most challenging step, ranking the groups by atomic weight at first point of difference. So we've got hydrogen, carbon, carbon, and carbon. Obviously, hydrogen is the lightest atom, so we can automatically make it group 4. Now, all those carbons are the same though. Let's move 1 bond length away to see if anyone finds something heavier. So this blue one up here equally meets 3 hydrogens. This one in yellow reaches 2 hydrogens and 1 carbon, and the one in pink here has 1 hydrogen and... How do we count double bond carbons? We need to be able to compare everything. Oh, thank you, Sketch. Double bonds count as having a bond to 2 carbons. So this pink side theoretically reaches 2 more carbons within 1 bond length. The same would apply to triple bonds, by the way, but you view it as a bond to 3 carbons, for example. So let's note what we have. We've got HHH in blue, HHC in yellow, and HCC in pink. Who has the winning hand? Well, 3 hydrogens is pretty bad. Those are not heavy to get a good rank, right? This one in yellow at least reaches 1 carbon, but this one in pink technically reaches 2 carbons. Looks like the pink side had a hand that beats the others. So, step 1 and done. All 4 groups are ranked by atomic weight, considering any tiebreakers. Do you remember step 2? Yeah, we've got to hide the back and find that spin. So with that dashed group hidden a bit there, follow 1 to 2 to 4, so we've got to spin to the left. This leads right into the quick step 3. Following that arrow, it is moving like so, counterclockwise, so you can write S. Alright, are we done? Nope, we've got that one last important step. Check that dash. If 1 or 3 is in the back there, we have to flip our answer. And look, that's rank number 3. So our S is actually an R. Awesome work there. Let's try the one below. So, step 1 again to rank. Those are our first atoms, carbon, 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 and hydrogen. Again, hydrogen sucks, so it's rank 4. Now, the 3 carbons can't be differentiated, so move to the next bond out for a tiebreaker. You've got 3 more carbons from that tert-butyl, 2 hydrogens and 1 carbon on the right, and 1 hydrogen with 2 carbons technically on the left. So out of all of these, who has the winning hand? If you're ever unsure, you may have started to notice hydrogen is not the priority. The more hydrogens, the worse the hand. So look, 3 carbons definitely beats out the other 2 sides that have a hydrogen taking up a spot. And keep in mind, sometimes people want to always prioritize the double bond, but it doesn't work that way. Tert-butyl got to heavier things first, so you have to check the hand that was given. Keep any ideas about IUPAC naming or reaction priorities out of this concept. So the order is shown here. We can move to step 2 now. Hide the dash and trace the numbers. Alright, 1 to 2 to 3, that's spinning to the right. Now step 3, which letter should you give it? Right or clockwise is R, so draw an R. Finally, step 4, which rank was in back? Oh, just group 4, so keep your answer, it's just R. Alright, so it really just takes a lot of practice, but you might be getting the idea. Let's recap. Remember these 4 key steps and the trick. 1. Rank groups by weight at first point of difference. Remember, check just 1 bond length away at a time and treat it like a winning hand of cards like in poker or something, rather than trying to add up any weights. It's never about the sum of masses, it's solely who got to something heavier first. 2. Hide the back or dashed group and trace the numbers you see. Ensure you're hiding the dash that is literally on the chiral center. 3. Write the configuration. Right or clockwise is R, and left or counterclockwise is S. And 4. The trick. Check. If rank 1 or 3 is in the back, flip your answer. Note that when you're checking the dash, it must be the dash directly on the chiral center, not a dash down the chain somewhere. These 4 steps can solve most instances of R and S configuration in molecules that aren't more complex in 3D shape, by the way. So things that are depicted in different ways like a Fisher or Newman projection. So with that in mind, let's go on to your practice. Give these a try. Find the R and S configuration of all chiral centers. I did throw in some more challenging ones here, so Sketch suggests you pause the video here to work it out. Alright, here are the answers. If we had to do a 1-3 in the back flip, I showed the original spin crossed out. If there's no configuration written somewhere, that means it wasn't a chiral center. So you'll have to look carefully. If you have any questions, feel free to ask below. So that is that. I know it's a challenging topic, but the more you practice, the faster and more accurate you'll get. If this helped you at all, feel free to like the video for some support, and if you want more organic chemistry help, check out my channel and feel free to subscribe. Great job today. See you again soon. Bye.